morning, welcome to new lecture. Today I will talk about Muller-Breslau principle, and we will draw influence line using Muller-Breslau principle. So our topic today is constructing influence lines using the Muller-Breslau principle. Let's see how we can draw influence line using Muller-Breslau method or principle. This method will provide us with tools, and using this tool we will draw influence line much faster. You saw in previous video we draw influence line using equilibrium equation. We can do that, always we can do that, and if we apply that equilibrium equation right, we will draw that influence line right. But that will take time. If we use Muller-Breslau method, we can do calculation much faster. So the reason we are using this method, because we will save time. So I can say Muller-Breslau principle allows us to draw influence lines faster than if we use the equilibrium calculations. Okay, how we will apply this method? I will write step by step, so you will follow exactly these steps, and we will practice. After applying these steps and practice, you will be able to draw the influence line immediately. It is very easy. So the basis of the Muller-Breslau principle is that we can find the influence line for a determinate beam by first removing the restraint caused by the parameter that we want to find the influence line So first step, we will remove the restraint caused by the parameter that we want to find the influence line for that. Second step, displace or rotate the resulting structure by 1 unit. First step, we will remove the restraint for that parameter. We want to draw influence line for that parameter. Second step, we will apply unit displacement or rotation at that point. Let's see when unit displacement and when unit rotation. I should remove this because I don't have space. Okay. If the restraint that is removed is an internal shear or a vertical or horizontal support reaction, then the second step is to displace the structure at that same location. If the restraint that is removed is an internal moment, then the second step is to rotate the structure at that location, at that same location. For example, assume I have simply supported beam. I want to draw influence line for reaction at point A. First I will remove that restraint. It means there is no reaction at point A. In that case, point A can move in vertical direction. Then I will apply unit displacement at point A. I will take point A and I will move up 1 unit. So how structure will deform? I will draw the deformed shape of structure. Will be like this. This will be influence line for reaction at point A. Influence line for reaction at point B. I will remove support at point B so it can move point B in vertical direction. I will move up the point B 1 unit and I will draw the deformed shape of structure. Deformed shape of structure will be one triangle like this, R, B positive. Let's look at 2 different examples. So I will start with simply supported beam. A, B, C. First, reaction at point A. Remove reaction at point A, move in the positive direction of the reaction and draw the deformed shape of structure. Reaction at point B. Remove support at point B, apply unit displacement at unit B and in the positive direction of the reaction and draw the deformed shape of the structure. Shear force at point C. In order to cancel shear force in any location, if we use this kind of connection, left and right, they can move respect to each other in vertical direction. You can take this up or down, you can take this up or down. So shear force will not transfer from left to right and right to left. So you will, any location you wanna draw influence line for shear, you will put this kind of node over there. So you will remove that restraint. You will remove shear force at that point. Then left side, left side. You will move up, right side you will move down. So you will put this kind of connection over there. This side move up, this side move down. Let's see how I can do that. I will put here, then left up, right down. If the location of B, C from this side is A, this side from is B, this part will be A over L height, this part will be B over L. If you add together A over L plus B over L, you will get A plus B over L. This is L, L over L will be 1. So you see, you applied unit displacement. If you add left and right displacement, it is equal to the unit displacement. And up positive, down negative, you will see the structure from left and right side of this connection, they should be parallel. So this line should be parallel with this line. Let's draw moment influence line at point C. So we should cancel the moment at C. Internal moment at point C should be equal to 0. So we will put hinge over there. Then we will rotate this side counterclockwise, this side clockwise, like this. Clockwise, counterclockwise. And we will draw again a form shape of the structure. This angle should be equal to 1 radian unit angle. And this height should be A times B over L. If I do the same thing with one cantilever beam, influence line for reaction at point A, for example, you will remove reaction force at point A and you will apply unit deformation at point A. So if you, because here we have moment reaction and force reaction, you should remove only force reaction. So here you should put this kind of connection, and here you will not cancel moment, only you will cancel the force, and you will apply unit displacement, so entire beam will shift up 1. If you want to draw moment influence line at point A, in that case you will put hinge here and you will apply rotation like this. This side cannot rotate because you attach to the support. This side will rotate, the form shape will be like this. Now, because one side is rotating, this angle should be equal to the unit angle. See the difference here? Because left and right, they are rotating both. This angle should be unit. Here, because one side is rotating, this angle should be equal to the unit rotation. We will practice. We will look at a lot of examples, so it will be easy to understand. Let's look at one continuous beam. Let's look at this beam. This is continuous beam. Point A. Here we have one support. B. From here to here it is 5 meters. Then You have hinge here, 8 meters. You have another support here, again 8 meters. I should make this beam a little bit longer. Here we have another hinge from here to here, 5 meters, and the last part, it is like cantilever beam, this is 5 meters. So A, B, C, D, E, F. Let's look at two different influence lines in this example. First one, reaction at point B. You will remove support B, you will apply unit displacement, you will shift up by 1 this point. So if you shift up this point 1 unit, what is the deformed shape of structure? Deformed shape of structure will be something like this. This is 1. From point C to point F, it will remain horizontal line. It cannot get any deformation, because in order to have deformation, this point C should move down. If point C move down, point E should move up. If point E move up, this part should rotate respect to F. And because it is fixed support, it cannot rotate. So from here to here, it will remain one horizontal line, and you will have deformation only in ABC part. The height for B will be unit. The height for A you can find from similar triangle. Always you can apply similar triangle rule. This over this height, which I don't know, for example, 1 over y, if I assume this is y, is equal to 8 over entire length. So this part in triangle over this is equal to 8 divided by entire length, that will be 13, 8 over 13. From there you can find y. Y will be 1.63. So this height, you can find it. It will be 1.63. Let's look at the influence line for reaction at D. Reaction at D. You will remove this support. You will shift up by unit point B. So how this will deform? If you remove this and you will move up, the point D, for example, will go up here. This is 1. This part will rotate respect to E. Because this is continuous from E to C, you should show it one continuous line up to C. Something like this. It is one straight line. Then, if point C move up, this part will rotate respect to B, point A will move down. Something like this. So, if this is 1 from similar triangle, you can find this height. This will be 2.6. From similar triangle, you can find this height. It will be 1.63. We draw these influence lines by assumption of 1 unit load moving on this beam from, for example, left to right. The question, if instead of unit load, the magnitude of the load, it is different. For example, 10 pounds, 20 pounds, 100 pounds, or P pounds. If I draw, for example, this influence line for reaction at point B, where I should put that traveling load in order to find maximum reaction at point B, it is clear you will put here the maximum height. So, what is the reaction at point B? The magnitude of the load P times the height. If you put here the magnitude times height here, if you put from here to here magnitude times height, which is 0, so if you put load from here to here, there is no reaction at point B. In order to find maximum reaction at point B, you should put load here, and magnitude of the load times the height will give you the reaction. This is for concentrated load. For distributed load, we should multiply the intensity of the load under the intensity of the distributed load to the area underneath of that distributed load. For example, if distributed load length it is 5 meters or something like that, the intensity is W. We should multiply W intensity times the area underneath of that in influence line will give us the reaction at point B. So the intensity W to the area underneath of this from A to B. If this load, you see this load will occupy from A to B. So the area from A to B in influence line you will find, you will multiply to the W. Of course I will prove that Y area, I will prove that later. But here only it is good you know from now, but I will prove it. So let's continue. So I draw influence line for reaction B, I draw it for reaction D. Now for reaction F, I want to do that. For reaction F, you see it is fixed support. Two reactions I have in the fixed support, one of them moment, one of them force reaction. I want to do for force reaction. So only I will cancel the force reaction. In order to cancel that, you should convert that fixed support to this kind of support. You will apply unit displacement. If you apply unit displacement, this EF part will move up and it will not able to rotate because you see the kind of connection you have. It cannot rotate. So this will move up by 1. Then this part, it is continuous, it should rotate respect to the D, it will rotate respect to the D. Here we will have one straight line. This is 1. From similar triangle you can find this is 1.6. And AC part, it is continuous, it will rotate respect to the B. So you will draw one straight line, it will pass from 0 point, you will continue like that. And here again this will be 1. From similar triangle you can find that. Let's look at two more influence lines here in this example. Sometimes I use metric unit, you see SI unit, meter, sometimes US customary system. So pay attention to the unit, but regardless which unit you are using, the concept, the procedure is the same. Okay. Let's look at to the influence line for moment at point F. So at point F you will put one hinge and you will apply rotation in this direction, positive moment direction. And because this part it is ground, you cannot apply, so only EF part will rotate. Because one side only rotating, this angle will be 1. If this angle is 1, from here to here it is 5. This height will be 5. Because tangent of this angle will be 5 over this. So this is 5, this should be 5 in order to have this rotation equal to the unit location. So this part is continuous, will rotate respect to the D, straight line, will rotate respect to the D. If point C move up, this part should rotate respect to B, like this. From similar triangle you can find this height will be 8 and this height will be 5, negative, positive, positive, negative. So this slope means rise to run always, and if one side rotating, that angle should be equal to the unit. If both sides is rotating, the summation should be equal to 1 unit angle. I will show in different example. Let's draw shear force at point G. Point G is here. I find a location for point G. Point G is here. 2 meters from this side, 3 meters from this side. I want to draw influence line for shear force at point G. So at point G, I will put this kind of connection. At point G, I will put this, then move, let's see, this side will move up, this side will move down. I think before I draw one picture, I made a mistake. I made mistake over there. Yes, I think I drove in the wrong direction. Of course, because of the contract, the positive, negative, different book, they have different contract, but we will follow this. So this side move down, this side move up. If you apply this kind of deformation, what you will get? This part, it will move up. So like this. Here is 0. From here to here, it is B over L. This height will be 3 over 5. From here to here, it is A over L. This will be 2 over 5. Continuous will move up. So from similar triangle you can find this will be 1.6. Double check these numbers. I'm not sure, maybe I made mistake. 1.6 and this is 1. So, and this is the location of the point G. The point G location was here at 2 meters. So at that point you want to draw shear influence line for shear force. You will plug this kind of connection, and this side downward, this side upward. I will double check my contract, because for a long time I haven't practiced to see which direction is right. Of course I can figure out in one simply supported beam. Just a moment. If I apply, for example, influence line here, and I move this side down, this side up. This should be right. This should be right. That will be positive. After that, negative. This should be right. So follow this contract. Again, if I made mistake, I will correct it, but for now, I feel this is right. Okay. And you see, the summation of this part and this part should be 1. And these parts should be parallel. And you see, they are parallel. Let's look at the influence line at point H. I should add 1 point again in the same beam. Point H. Point H should be here. Point H. I want to draw influence line at point H for shear force. So again, I will apply this kind of connection here. This side up, this side down. If you move this side up, this part, in order to move up, you should separate from this support, and that is not possible. So this part is 0, 0, up to here, point H, no deformation. So entire unit deformation will be like this, up to here. And this AC part will rotate respect to be like this. And this will be unit 1. This will be unit 1. If you plug this here, let's say do that, maybe you have hard time to understand. Now, move this down, this is up. If you want to move this up, how it will move up? This should rotate respect to the D, or you should separate from D. Because if it rotates respect to the D, this point E should move down. In that case, this EF part should rotate respect to this support, which it cannot do that because we have fixed support. So it cannot rotate. On the other hand, if it wants to go straight up again, we should have rotation here, which we cannot have rotation, and you should separate from this support. We cannot do that. So this part cannot move. But if you move this down, this easily can move down, and this part will rotate respect to B. So this will be influence line for shear force at point H. Okay, influence line for bending moment at point G. Influence line for bending moment at point G. This point, you will apply hinge, you will cancel bending moment over there, apply rotation in the positive direction. And now for sure I figure out this direction is right. Previously, in other example, that direction I show, it is a wrong direction with this sign convention. Because I will follow this sign convention, you will follow this kind of movement. For moment, you will put hinge here, and you will apply rotation. If you do that, if you plug hinge here, let's see now, this is continuous, and you have hinge here. Apply rotation. What will happen? Point G will move up. This part will rotate respect to E. This is 0. This part can rotate respect to the D. Point C will move down. AC part will rotate respect to B. Straight line. Now you see both sides, they will rotate. Now this angle should be equal to unit rotation, and this height should be equal to, you can prove it, A times B over L. Last session, using equilibrium equation, I showed that this should be AB over L. This height should be AB over L. A is here is 2 times B, it is 3, L it is 5. So that will be 6 over 5 will be 1.2. If that is 1.2 from similar triangle, this is 4.8 and this will be 3. I think for as an introduction, this example is enough. Let's look at one more beam with overhanging part maybe. Maybe it is good to, for now, I review this example as well. We have one very simple example. Simply supported beam with overhanging part A, B, this is point C, A, B, this is C, this is D. Okay, we want to now find influence line for reaction at point A. You will remove point A and you will apply, or you will shift up by unit point A. So it will be like this. This is one. From similar triangle you can find that height. Influence line for reaction at B, you will remove support B, shift up by 1. So this is 1. Oh, sorry. This is 1. From similar triangle you can find this height and this height. Okay, shear at point C. So plug this connection down, up. Okay, if you do that, this part will move down, this part will move up, then this will rotate respect to support, this will rotate respect to support, this will be A over L, this will be B over L. These parts should be parallel, and if you add A over L plus B over L, it will be equal to the unit. So this will be shear at C, moment at C, you will put hinge. At point C you will rotate like this. If you do that, you will get this kind of deformation, and this angle will be unit angle, and this height will be AB over A plus B or L. Okay, in order to find the magnitude of reaction or shear force or bending moment, if our traveling load magnitude it is not 1, I explain if it is P, we will multiply P times the height underneath of that. If it is distributed load, assume you have simply supported beam and you have distributed load and you draw the influence line. Part of the influence line is like this with horizontal. If you look at one element in the x distance, this is dx for example, a small element. Let's look at the influence line in that element. This is dx, this is x. Here entire resultant force will be, here entire resultant force on this element will be W times dx. So the resultant force will be W times dx. If I multiply, this will be like one concentrated force dF. So I should multiply dF times the height underneath y in order to find the reaction or shear force or bending moment, depending on which influence line is this. It is influence line for shear force or bending moment or reaction. So I will multiply the concentrated load to the height underneath. Concentrated load, distributed load in a small element will produce concentrated load because the intensity of load times the small element, very small element length, which is dx, will be dF, the small force in that element like concentrated load. If I want to find the magnitude, I should multiply that concentrated load to the height on influence line. So if I plug instead of dF, from here, W times dx times y, this will be W times integration of y dx from 0 to L. This means this is dA, the differential area. If I integrate it, I will get entire area. So if we have distributed load, you will multiply the intensity of distributed load to the area underneath of that distributed load in influence line. For example, distributed load length is equal to B and intensity is W. You will find the area in influence line for B. After finding this area, you will multiply that area by intensity of distributed load W. So you will find the magnitude of shear force or bending moment or reaction. I think for today is enough. Next session I will cover several examples regarding influence line, and step by step you will get master in this topic. It is very easy. Pay attention to the concept and follow those steps. Practice, you will see it is very easy. For any complicated structure, using Muller-Breslau method or principle, you can draw influence line in 2-3 seconds. It will not take long time. Of course, it is possible sometimes you do mistake. Even these days, sometimes I make mistake. That is not problem. But if you practice, you will be master in this topic. It is easy concept. Thank you so much for watching this lecture. See you next session. Bye bye.